Everyone, I'm Sri. I'm one of the coaches for FRC team Future Martians. Welcome to our FLL Advanced Coding Camp for 2026. We do these every year, and it's an exciting time, especially since the season has just been started. You know, the mat has been revealed, and a lot of you might have already received your FLL mat and missions. So it's an exciting time to be getting into this. So with that, I'm going to introduce Ramesh here, who's going to introduce the team and kick off the camp. Okay. At any time, please feel free to ask us questions. Few minutes through, we will talk to more of you, like get more introductions, but we want to spread that across the camp. So we're going to go ahead and get the presentation started now. And we will be recording this. So again, videos are completely optional. You don't have to be on video if you didn't want to. We will be posting this on posting the recording on YouTube, just so that you're aware. Sure. After you introduce the team, just pause for a moment. I'm sure on the room.
Okay, yeah, sure. Okay. Hi, everybody. I hope you're all doing well. My name is Ramesh, and I'm from the team Future Martians 1923, and we're very happy to be hosting this coding camp today. So, yeah, let's get started.
Yeah, you can go through this.
So, first of all, I would just like to kind of introduce the team here. So, we are actually a 5th-year FRC team, and we've mentored over 45 FLL teams in the past 4 years. And most of the students on our team actually have like FLL and FTC experience, and we've kind of over time worked our way up to FRC. And we've actually recently made it to the World Championships in Houston, Texas, 3 times in just 4 years of FRC. And we've actually won awards 2 times at Worlds. So if you guys have any questions, you can always just put them in the Zoom chat.
Okay. So we just want to show you so that you get a feel for what we have going on here in person. So we have the FLL mat set up with some missions, not all of them. We still have our members building some of the missions. And we will be using the mat here for some of, because we have members here who are attending in person. And we're expecting a couple more to show up here shortly. And we will be running some code on the FLL mat, whether it's turning or PID, just to demonstrate that. So whenever we do that, we will switch the camera view to the board. But at any point, if you haven't received the board yet, if you have any questions about the field, please feel free to ask, and we will be happy to point to the field with the camera or answer questions, zoom in into any specific part of the field that you want to talk about. Okay, with that, Ramesh, you can continue.
Okay, so let's just dive in a little bit to the hardware overview. So this is the Spike Prime brick. Basically, this brick is the robot's brain, and it controls all the motors and sensors which are connected to it. The brick has a 5x5 customizable light matrix, a speaker, and it can store up to 20 programs. The brick has about, I think, 6 input/output ports, and it also has a built-in gyro sensor. The brick has Bluetooth and micro USB connection options.
And at this point, I'll just add, if there are any mentors on the call, and if you had questions about Founders Edition versus Future Edition, definitely we'll be happy to talk about that, because we've had to do some finding out and helping teams decide what to do with respect to that. Because as of now, you cannot purchase the Spike Prime and expansion set from Lego anymore. It's basically, if you have one already, you have it. Otherwise, you have to look to teams that may have graduated to FTC to donate or sell you one, or maybe look on eBay. Other than that, of course, the expectation for this camp is that you may have already done FLL and you know block coding. So we're not going to get into the basics of moving motors using sensors. We will be going into more advanced stuff. But if any of you have joined in and don't have a lot of experience, that's okay. We will, the way we explain things, it'll still be knowledge that you can gain and utilize. But feel free to ask us questions if you have any as we're going through. And that's why we thought we'll start off with the hardware introduction, just in case somebody is new. And also it's a good refresher for anyone who may have just done it for a year or so. Right, unless you can.
Okay, so the next thing we're going to talk about are some of the motors that are involved here. So there's basically two types of motors, medium and large. So the medium motors are for like lighter loads, and they have a higher maximum speed than larger motors, and they're actually very compact. So if you wanted to use them as drive motors, you would need like a pretty light robot. Then the large motors are for high power, high torque applications, but are larger and slightly slower than medium motors. They would make better drive motors for like more heavier and bulkier robots.
And also you could, depending on the kind of attachment you're building, that is also part of the consideration. If your attachment is going to be taking an action which involves pretty high torque, you might want to consider the large motors even for the attachments. So basically, based on your design, you want to decide between the large and the medium motors.
Now let's talk about some of the sensors here. So first up is distance sensors, and they basically detect how far an object is like in front of the robot. So they have a range of about, I think, 200 centimeters. And then there's another type of sensors, which are called force sensors, and they detect the amount of force being acted upon them, which is up to 10 Newton. But they can also be used as like touch sensors, basically. Then another type of sensors are called color sensors, and they basically measure like reflected light, and they're able to distinguish between 8 colors. Then there's another type of sensors called rotation sensors, and they're also built into the motors, actually. Then there's also an inbuilt gyro sensor, which we will cover next.
So before we jump into that, distance sensors and force sensors, which is the touch sensor, there are some creative applications you could use those for. I know some teams, they like to back into the edge of the FLL board table to make sure that they're level, as a way of saying, telling that they're perfectly at 90 degrees. Now, that used to be more common when with EV3 kits, the gyro sensor was useful, but there was the dreaded gyro drift. So many teams just refrained from using the gyro sensor with EV3 Mindstorms because they might have gotten burnt that just in their match, it might have misbehaved. So we want to make sure that you understand the new gyro sensor or the gyro sensor that's inbuilt into the Spike Prime kit. It is really reliable. So we have never encountered gyro drift using that one. So techniques like using the touch sensors, like 2 touch sensors to back into the FLL table, those are more older ways of doing things. Now the color sensor. So in years past, the table used to have a large number of those black and white lines, which you might see on the FLL mat. So back then, color sensors were definitely used a lot more than you see them used now. There are still teams that use them in very creative ways. Like, they have index cards, and all they do is just pass a specific colored index card in front of the color sensor, and it executes a different program. So rather than have the students having to go in and use keys to browse through and then hit enter to start a program, instead, you just show an index card and it will execute that specific program. So there's creative ways you could be using color sensors like that. And there still are a few places you're going to see black lines and black and white lines on the current season's FLL mat. So you could you could use color sensors to approach that and then level yourself if you would like to do that in addition to using the gyro sensor. And it definitely helps you get to a specific spot and you know for sure that you've reached that, irrespective of if your wheel spun and you lost some rotations because of that spinning. Irrespective of that, you can keep going till you reach a black line or a white line and things like that. So there's definitely still uses for the color sensor. And I keep saying still because the gyro sensor is by and large the most used sensor with the Spike Prime. And most of our camp will actually be utilizing the gyro sensor. If you're using color sensors, and in fact, for our example here, we're going to be using the advanced drive base, which does have 2 color sensors installed for using. And if you're using the advanced drive base and have uses for the color sensor, that's definitely a fine thing. And rotation sensors, what do we mean by that? It's basically the motor's ability to track how many rotations it's turned and report that back. Or you tell it to turn a very specific number of rotations, and it does that. That's the whole rotation sensor. Or you could, in other first programs, we call it encoders, motor encoders, and things like that. But essentially, the motor has a way of sensing how much it has turned, and that's what the rotation sensor is. And you use that all the time because many times you are asking your motors to turn a certain number of turns to get to a specific spot. So with that, like we said, the gyro sensor is the most important one. And in the next slide, we're going to talk about that in detail.
Okay, so this is the gyro sensor. So the inbuilt gyro sensor has a 3-axis gyroscope and a 3-axis accelerometer. Sorry for my pronunciation, but the gyroscope can measure the pitch, roll, and yaw angle of the Spike Prime brick, and it can also determine the orientation of it, like the front, back, or the top, the bottom. Then the accelerometer allows gestures to be detected, whether like shake, or tap, or free fall.
So the terms that you see there, the yaw, the roll, and the pitch, please do get familiar with those, especially if you plan to pursue further FIRST programs. Those terms are used all over. And one more thing, so just by the orientation of that brick right here, if you're making turns, you're going to be taking into consideration the yaw, because that's what shows you the rotation along the flat axis, right? Along the flat plane. Which is parallel to the FLL board. But if you happen to build your robot in a manner where the orientation of the Spike Prime brick is not the way you're seeing it, let's say you're building a box robot and you happen to put your Spike Prime brick in the back like this. So in that case, you're going to be considering, like if my palm here is the width of the Spike Prime brick, you're going to be considering the pitch for how much the robot has turned. If you're this way, you're going to consider the yaw. So please remember that this is part of the settings at the beginning of every program. So depending on how your robot has been designed, you need to set the right, or basically indicate which of these are going to be used when you're trying to check how much your robot has turned, whether it's the yaw, the roll, or the pitch. And then the accelerometer definitely creates some fun options. Not so much for FLL maybe, but if you're building something else for fun, you can definitely use that. And then going back to the yaw, roll, and pitch, about 4 or 5 years ago, there was a game where the robot had to climb over an inclined ramp and then go over. As soon as it straightened, it had to stop because otherwise it would enter the opposite field. You know how FLL, the games have the 2 fields together. So in order to stop it just before it enters the other field, you had to stop as soon as it straightened. So that was a good example of where, in addition to the yaw, you would actually use the pitch if you're considering what you have here, so that you know that when the robot is either angled down or angled up, and then it becomes straight again, you want to know as soon as that happens. So well, in this field we don't have anything like that, so it'll really be one angle along which you're going to work, and that's for the purpose of turning. Anyone have any questions regarding these various terminologies or just about the gyro sensor in general? Okay, and yeah, please post questions in the chat if you have questions. And other than that, feel free to go off mute and ask us questions. We will stop and answer. Okay, right.
So now I'm going to pass this off to Zainab. So this is the programming lead.
Hi guys, I'm Zainab, and I'm going to be telling you guys about the block sections and the extensions. So in Spike Prime, the coding blocks are organized into sections. There's motors, movement, light, sound, events, control, sensors, operators, variables, and my blocks, which we'll talk a little bit about later. So motors are to control the movement of individual motors. Movement is to control the movement of drive motors. Light is to control the light grid on the robot. Sound is to control the speaker. Events are wind blocks and broadcasting. Control is weight blocks, conditionals, and loops. Sensors, Rama's talked a little about sensors, and those blocks are for reading data from those sensors. Operators are for mathematical operations. And variables are for using variables that have already been created, and those are commonly used in the my blocks.
So they're of course color coded for convenience, so that's a good thing. And movement motors are one thing we want to make sure everybody understands how those work. You basically define your drive motors by indicating the pair of motors which are connected to the wheels. And then the movement motors always issue commands to both those motors at once. So the command works on both those motors at once. That's what differentiates movement motors from the regular motor controls. So that's one important thing to be aware of. And my blocks for mentors, it's basically like reusing methods if you've done regular coding. But we want to make sure that everyone is aware of what my blocks are, because we are going to be utilizing those here during the camp. If there's a piece of code, let's say you are making your turn happen very reliably, and to do that, you have a bunch of complicated code. Now, you don't want to be replicating that complicated piece of code. Like, let's say it needs 10 blocks to make a turn very reliably. You don't want to be copying those 10 blocks every time you want to make a turn, right? You instead want it to be just one block so that it's easy to use, but still uses all that complex logic you have there to improve the reliability. So you will put that complex piece of code together and define it as a my block. And once you have defined something as a my block, it becomes available on your palette on the left-hand side under the red category, which is for my blocks. You will see whatever name you gave it when you defined the my block. By that name, it becomes available. And you can also have parameters that you pass into my blocks. It's if any of you are doing any regular coding, it's like passing values, variable values into the method. And then apart from that, again, when we are using that, if you have questions, please feel free to ask us. But strongly suggest if you have not been using my blocks, you really should be, because for advanced coding, it makes it a lot easier. Does anyone have any questions about what we've covered so far on the block sections? Okay.
Okay, so now you can get out your laptops because we're going to be showing you how to add the extra blocks into Spike Prime.
So yeah, from here on, it's largely going to be a follow along. So we hope you all had a chance to install the Spike Prime app. If you haven't, you can get started now. By the time you need to start adding code, you should be able to get it installed by then, especially those who are remote. For those in person, I don't know if the bandwidth will support everyone trying to download. Do you all have Spike Prime app installed? Okay, perfect. So you may or may not be aware, but there's this concept of extensions. And if you look at this part here on the shared screen, so the part that's circled in red. So if you scroll down where you have, or the bottom left-hand corner of your Spike Prime app, you will see that icon. And when you click on that, it's going to open up a dialog or a page where it shows you some of those values like more motors, more movement, music, line graph, etc. So by selecting that, you are installing extensions, and those come with a whole bunch of blocks of their own, which you would use for those purposes. So for example, if you were to select more motors or more movement, you will find that now you have more blocks available on your palette on the left-hand side than you did before. And we use some of those more advanced blocks, so we require everyone to have at least those two extensions enabled. Feel free to add more extensions and play around with it if you would like to do that.
Has everyone been able to add the extensions online and in person? You also just like start a new.
So yeah, let's keep an eye on the chat. And I'm going to request one of the Future Martians members here to stay on, get on Zoom, stay on the laptop so you can keep checking for messages if people have questions. Could you please show us code for drawings? Going straight in. Yes. So we will be, there was a question about, will we be covering some code for going straight using gyro? Yes. Some of the more important things or most important things we'll be covering are going to be, first we'll start off with just the regular gyro turn, just to make sure everyone's comfortable with that. And then we're going to talk, get you guys to code proportional decelerating gyro turn. What that means is as you're turning and depending on how many degrees of turn is left, it starts slowing down so that it doesn't overshoot the turn. So I don't want to give away what we're going to do, all the other stuff, but that's going to be covered. And then we're going to cover proportional go straight. So we're going to use, so PID, I'm kind of jumping ahead here, but yes, we will be covering the parts where you will be able to use the gyro to go straight and turn very reliably. Okay, so we are just waiting to see if everyone got the extensions. So I'm just going to bring up the.
You guys can give thumbs up if you guys have managed to do this.
Okay, so yeah, please give a thumbs up if you have managed to add the extensions or already had it added. So we saw about 4 thumbs up. So we're going to wait, or let's do this. We will switch to the program on our end and make sure that you guys get a chance to see what we're talking about exactly. And hopefully that helps. We'll switch to the program and so everyone, if you can look at the shared screen at this point, and you can see I'm kind of hovering the mouse pointer over the bottom left corner. So that's the button you want to click on. And when you click that, it's going to bring this up. And then you want to select at least more motors and more movement. You can do more sensors and things like that later if you want, or if you want to do it now, that's fine as well. And all you do is select those, and it should install those. And then you close. And if you go back and check, you'll see some new options available under the specific categories in the palette. Okay, so let's quickly check again. This time we're just going to say if anyone has not yet added extensions or would like help, please show us a reaction in
Raise your hand.
in Zoom. Yeah, raise your hand in Zoom, and we can go from there. Okay, so no one has raised their hand, and I think everyone here in person, you all have the extensions enabled, right? Okay, perfect. Oh, okay. We have two hands. So
No, they're just doing both.
okay, let's actually confirm. So Arjun and Anderson, if you guys were giving, and I think Sarah,
Yeah.
my glasses. Yeah. So yeah, we saw 3 thumbs up. If it is actually because you would like us to just show that again. Here, let's do that again. So switching back to the, or I guess in the shared view, you're already seeing Spike Prime app. So bottom left corner, where we are hovering, there's a little icon. You click on that icon, and it's going to bring up a dialog with a few rectangular area, options. You want to select more motors and more movement, and then you can close. Okay. All right. So with that, let's move on to the next slide. To resume the slideshow.
Has to get on to.
Turning the chair. Okay.
Hi, everyone. My name is Isha. I'm the Vice President of Future Martians. I'll be going over some more advanced programming concepts. So first is the basic gyro terms. This is a basic term that uses the gyro sensor. Basically, the my block has an input of the target angle, which is what you can choose to determine how much the robot should turn. First, you set the yaw to 0, set your movement motors, and set movement motors to brake.
Let's take it slow. So because we want them to follow up.
Okay. And movement motors to brake and the movement acceleration to smooth. And what this does is it improves accuracy. Then you can start the wheels moving to turn right and continue until the robot reaches 5 degrees before the target angle and then stop moving. And this is done to account for overshoot due to built up momentum when the robot suddenly stops. And then the reason why we make this a my block is so that it's easy to reuse as one simple block. This is a right turn, but for a left turn block, the movement speeds would be opposite, so they would be negative. Does anybody have any questions about this? Feel free to put them in the chat or just raise your hand. Okay. Okay, we can move on.
Yes, we can start.
Wait.
So you want to switch to the app and start recreating?
Should we?
Yes, yeah, so at this point, we would like everyone to start making the same code. So yeah, so this is what we have in our Spike Prime app. So please go ahead and start building this. And we have our chat open, and let's also get the videos open so we know, or for the place where you can react open. So please raise your hand if you have a question, or send a chat message, or unmute and ask us.
Should we give them like 5 minutes?
Yes.
Okay, so do you? Okay, it's 2:30 local time here, so we'll give you until 2:35, and then we'll check and see who has the code written down.
Right. So just to kind of talk about some of what we have here. As you see, this is how you define a my block. So that's the definition of a my block there. And basic gyro turn right, that's the name of your my block. And then the target angle, so that's a variable. So whenever you use this my block, you need to provide a value for it. And that value is the target angle to turn to, right? Or how many degrees it should turn by. So that's what you would have to provide. And then setting your angle to 0, so as we indicated, we are going to be using a robot, and let's actually show what it looks like. So this one here is the advanced drive base. And as you can see, it's built up so that the Spike Prime brick is basically flat like we saw in that diagram. So it's going to be the yaw angle which decides the turning of this robot. And which is why the yaw angle is being set to 0. Now, if you had a box robot where this brick was actually on the back of the robot with the white part facing outward and back, then you would be using the pitch or the roll. So please take a look at that and then decide whether you want to set the yaw angle or set the pitch angle based on your robot's design. Now, if you have your robot with you, we strongly suggest testing these programs out. If you don't have a field, an FLL mat, that's okay. Just have a clean surface on the floor where you can run it, because all the programs that we run today, you can do that on just a clean floor. And then that's the yaw angle. And then as you recall, we were talking about the moment motors, which require you to set a pair. So you're defining a pair of motors. And what do we mean by pair of motors? We're indicating the ports to which those two motors, which are going to be your drive motors, are connected. So you identify that pair. It doesn't have to be A and E for you guys. It might be a different one based on how you connected your robot or how you wired your robot together. So please make sure you are doing that right. And also, A plus E is not the same as E plus A. What that means is you want to define the motors. So imagine you're looking at the robot from top with the front of the robot facing up. The left-hand side would be the first one you indicate. The right-hand side is the second one you would indicate. So please make sure you're following that. And then set moment motors to brake at stop. So the expectation is you would know what these mean, but let's talk about it. When you have it set to brake mode, what it means is when the command is executed, it's going to hard stop. It's going to stop right at that point when the command execution is complete. Whereas if you set it to coast, then what happens is it's just going to keep, it has reached there, but it's not going to put a sudden stop. You could have a subsequent command which requires the robot to keep moving. A classic example of this is, let's say you built your code so that it starts off slow and then starts going faster. So maybe the first 2 rotations were happening at 50% speed, and then the next 5 rotations happen at 75% speed. You don't want your robot to stop and then start accelerating to 75%. That defeats the whole purpose of starting slow and accelerating, right? You want it to be in a mode that's not brake. And coast would be perfect, because then without stopping, it just segues on to the next command and keeps moving. But in this case, we want to stop after a turn. You don't want it to just keep turning after it's done with the specific amount of turn you wanted it to. And that's why you would set it to brake mode at stop. And acceleration, definitely for turning, we would suggest staying with slow, just so that you have more reliability. When you go with the other advanced turning mechanisms, you could change that. But given the fact that when you decelerate to a stop anyway, keeping it at slow would not make a huge difference. And then target angle. So you already explained this part. So okay, so the loop, what we're doing here is when you get closer to where you're going to stop in the last 5 degrees, you're going to step down the amount of power that's being used so that you're not turning at full speed and overshooting and continuing to turn further. Now, this is a good way to have it be better than just turning and trying to stop at the exact angle. But we're going to, in the next program, do even better than this and work with proportional turns. But this is a good way to work with a simpler turn, where when you know you're close to stopping, you slow down your turning speed. Okay. So the rest is kind of self-explanatory. You basically want to make sure that you keep turning till you have reached or exceeded your target angle. Ideally reached, but you want to also cover the exceeded, because if it doesn't read it exactly at the point where it's equal and you do not have the exceeds, it's going to think, oh, it's not equal, so I'll keep turning, and it's not going to stop. Okay, if anyone here needs more time or hasn't yet completed putting that code together, please let us know. Also, a quick question, if you guys don't mind, how many of you have a robot on which you can be testing the code that you are writing? Can you please raise your hand if you have a Spike Prime robot that you will be testing your code on? So what we will do is, okay,
Could
I have one hand.
I think one person does have those Spike Prime.
Okay. Well, actually, only one person raised the hand. So what we're going to do is when we execute this code here on our demo robot, we're going to point to the field and show the behavior. So let's work with that. So please keep your eye on the camera view also so that you can see the behavior. Since everyone seems to have completed writing that piece of code, let's go ahead and run that program on our demo robot here.
They're still writing.
Okay, so we will ask you guys to hold on for a couple of minutes. We have the in-person members still putting that program together, and they are going to be testing their code on the robot as well. So while they're finishing up, we can definitely run it on our robot and show them. So get that closer to the camera. You could use the grid to show them.
So I'm gonna make the robot turn 90 degrees. So let's see it's
Wait, why are we setting?
because that's how it is.
Oh, there is a question. Why are we doing target angle -5? Can you guys explain?
Yeah, so the reason why we set target angle to target angle -5, which is just to be clear, the red target angle is your input. So that's like, for example, I put 90 degrees in here. That's what that means. And then the orange one is our variable. So the reason why we set the variable to our input -5 is to account for overshooting. Because like we were talking about earlier, when you turn too fast, sometimes it can drift and overshoot a little bit. And then that way the angle you end up at is higher than your target angle. So it sets it to 5 degrees less than your target angle so that you have 5 degrees of wiggle room. And then you move at a slow speed until your yaw angle is greater than or equal to.
All right. So yeah, just to explain a little more on exactly that -5 there. So the way this is, so this number, the -5, could vary depending on your robot, depending on the behavior of your robot. So for some, it might be -2 or it might be -3. So what being done here is you kind of figure out what typically is the overshooting angle, like how much does it overshoot by? If it's 2 or 3 degrees that it overshoots by typically, that's the number you would use here. So what you're doing is preemptively, if you want to turn 90 degrees and you have a robot that always seems to overshoot by 2 or 3 degrees, instead of giving a target of 90, you're giving it a target of 88 or 87 so that it stops actually at 90. Again, like we said, this is a crude way of doing things. This is just to illustrate a concept. We do not suggest you use this. And in fact, this is just a stepping stone before getting into the better way to make the turns, if that makes it clear. And so some of you, yeah, if you do not have a robot, that's totally fine, because large part of what we're trying to do here is explain the thinking behind how these programs are being constructed. And of course, we are going to demo them here. So anyone who doesn't have a robot, you can watch the robot's behavior here, and it should make sense. And we are happy to rerun it any number of times that you need. If you want us to run at different angles, we can do that as well. But going back to the -5, we hope that makes sense. Again, this is a very crude way of doing things, so please do not make this your actual way of turning in competition. So in this case, when we're trying to turn 90 degrees, essentially, because it's going to overshoot a little, you are saying, hey, just turn 85, not 90, because we know you're going to overshoot 5 degrees anyway. That's the thinking. Do you want to execute that there?
Yeah, well, I did, but I'll do it again.
Yeah, do it a few times so that.
We can do, let's do 45 degrees.
On the 45. Yeah, so it is adding up. The errors are adding up.
Yeah.
Right, yeah. You do a 180. So it still overshot maybe a couple of degrees.
So one thing I want everybody to notice about the way the robot is behaving while we're running this code is that it's not actually slowing down much. If you look at it, it's kind of going the same speed during all parts of the turn, which I will show you why that's not as good when we go into our P control gyro turn. Okay. So if there are no questions, we can move on to P control now.
So since this is a simpler program, just to explain a concept, we're not going to have all the in-person people run it, but from the next program onwards, we want you all to test out what you wrote on the program. Okay.
So now on to P control. So the P control is basically a decelerating turn, and what it does is it uses the gyro sensor to slow down the turning speed as the error reduces by using a proportional algorithm. So let's break it down. The error is how many degrees away from the target angle the robot is. So mathematically, that means remaining angle of turn equals target angle minus current angle.
Just want to add something here. The word error, it can really throw you off and make you think of it as something different. Unfortunately, that's the industry term that's used, error. But what it really means is, what is the remaining turn? So you have an intended value you're trying to reach. How much more is left to reach that? That is what error is. That's an industry term which is not very intuitive, because it makes you feel like, wait, are we having an issue here and we're trying to measure the error? No, it simply means how much more is remaining, just to clarify that.
So in a P control turn, speed is proportional to error. So that's kind of what I was talking about earlier. Basically with P control, okay.
You hit the backbone.
Okay, with P control, the robot actually slows down the closer it gets to its target angle. So the less the error is, the slower the robot gets, and that way that prevents overshooting. So, okay. So at first we set the error to target angle because the robot has not moved yet. So if you think about it, if your yaw angle is 0, and your yaw angle is your current angle. So if that's 0, but your target angle is 90, then your error is 90 degrees, right? Because you haven't turned it all. And then, okay, the proportional algorithm is used to calculate speed from error. So speed equals the proportional constant times error. So in this example, we have 0.5 as the proportional constant, but this constant, kind of like the -5 degrees we did in the basic gyro turn, that needs to be specifically tuned for each individual robot. So your P constant might not be 0.5, it might be 0.8 or 0.4. So that's something that testing is needed for. Okay, if the speed is positive and lower than 5, the speed is set to 5. And if it is negative and greater than -5, then it is set to -5. This is called a lower bound clamp, and it is done because the motors will not run at a lower speed. So that is this part right here. And what that means, basically with these motors that we have with Spike Prime, when you run it at too low of a speed, they start to not move accurately. So what it's saying is if my speed is less than 5, which is calculated by the p constant times the error, if that number becomes less than 5 for the speed, then I'm just going to set it to 5, because if I run it at something lower than 5, it's not going to be accurate. Does that make sense to everyone? That can be confusing. If you have any questions, drop them in the chat.
Does anyone in person have any questions?
Now you can.
Okay, moving on. So the motors are set to move at the calculated speed. Once the robot heading is within 2 degrees of the target angle, the robot stops moving. If we did not include this tolerance of 2 degrees, then the robot would have to hunt for the exact target angle, meaning it would constantly go back and forth in small amounts until it reaches the exact angle. And if this happened, then it would waste a lot of time on your mission runs, and it would just be inefficient. That's why we add a 2-degree tolerance, which is what it's saying right here in this line. Okay. The absolute value ensures that the loop condition works for both positive and negative error values. If error and speed are positive, the robot turns right, and if they are negative, the robot turns left. So what this does is it's saying if the robot overshoots the turn, then it has a way of correcting it and bringing it back so that it can meet the target angle. So how this is different from our previous turn is the other one, it almost wants you to overshoot it, and there's no way to bring it back from overshooting. But this one, it calculates how much you need to get to your target angle, but almost also how much you need to lose to get to your target angle, depending on whether you undershoot or overshoot your turn.
So yeah, few things to note here. Yes, there's a bunch of code here, but to think of this in simple terms. You know that when you have a larger amount of turn to make, you can afford to be faster in the initial part of the turn. It's really when you get close to your intended angle, where you're close to being done with your turn, that's when you want to be more careful about how fast you're turning. So if you had a 360-degree turn for whatever reason, you can start really fast, 100%. And then when you get really close to where you have the risk of overshooting, that's where you want to be slower. This is why you are going to calculate how much angle is still to be completed, and that decides how fast your turn is going to be. And as you get closer, like was mentioned, if you overshot by 5 degrees, you want to bring it back. And that's an ability you're going to have here if it overshot. And the thing about the +2 and -2, it is there as a safety measure. But what we see is typically you almost never overshoot. And even if it did, maybe 1 degree at the most. But we have a tolerance there just so that, like Isha mentioned, you do not want your robot just going back and forth trying to reach the target angle when you're trying to get precious seconds saved there. So you can start putting this program together, but let's open up for questions about the code itself. So if anyone has any question about, okay, let's get back into the explanation then. So yeah, there's just one comment about, okay, so at this point, we're not really talking about PID yet. So PID will come in when we go straight. This is simply a proportional or P-controlled gyro turn. And bottom line, what that means is the speed at which you turn is proportional to the amount of angle that you have remaining to turn. So you start fast. As you get closer, you know that you have very few degrees of turn left. That's when you are slower. So that's where the proportionality comes in. And when you and the reason for that is you want to reduce the possibility of, yeah. So we will be explaining PID. That's in the upcoming slides in the next program. But for now, we would like you all to implement this, get it. If you have a robot, please get this working. And for those who are in person, please go ahead and implement this code, and let's have you test it on the robot here. So happy to explain again if necessary. So please send a message again if you'd like us to repeat that, or if you want us to just go through instruction by instruction again, we can definitely do that also.
Also, if there's a specific part that's confusing or you're not sure why the code actually has that, we'd be happy to explain that as well.
Right. And the absolute, like Isha mentioned, that is so that you can use the same piece of code both for your left turn and your right turn. So P control. Okay. So yeah, we will explain that in just a moment. So absolute, the function, the mathematical function absolute, what that does is whether you have plus or minus, it just gives you the value. So +5 and -5, both of them have the absolute value of 5. And that's what's being used there. But you do keep track of whether you're rotating clockwise or anti-clockwise, and that will be turning in the required number of degrees for that. So P control, yeah. P control, so the concept of doing something proportionally, right? P in P control or in PID, P stands for proportional. And what this means is there is something you're going to be tracking. There's something you're sensing and tracking, and you're taking action proportional to what you're tracking. So in this case, as you're turning in a loop, you're constantly going on measuring. You're going on asking the gyro sensor, hey, how many degrees do I have left to turn? How many degrees do I have left to turn? You're constantly asking. And since while you're asking, you're also executing the turn, the value that you're getting back from that command, so it's a sensor read command where you're reading from the gyro sensor. Since you're constantly asking as you're turning, it's going to keep returning reducing values, because since you're executing the turn, the amount of degrees left to complete the turn is also going to keep decreasing, which means you are getting a decreasing value back from that sensor read or from that command. And you are multiplying that value which you got to the power of the robot. And that's how much power you're giving it into the robot when it is turning, which means the power of the motors is proportional to the remaining degrees of turn. If you have more than 100 degrees of turn, you will be turning at 100% speed. But as you start getting to, let's say, 50 degrees of turn, then you have reduced your speed to 50%. Now, I don't know if the code is using exactly that, but this illustrates the concept though. And then when you have 20 degrees of turn left, you are multiplying 20% into the max power of the robots, which means you're making it turn at 20% of power. So you see how you're constantly reading to know how much turn is left, and accordingly applying the amount of power based on how much is remaining, which happens to be decreasing. So the speed that the turn is executed at is constantly reducing, proportional to how the amount of degrees remaining in your turn is also constantly reducing. I hope that clarifies what proportional control or P control means. Please let us know or give a thumbs up if that explanation was helpful and it makes sense now. Okay. So our in-person attendees, are you at a place where you have all the code written down? You are? Okay. So whoever is done, feel free to go ahead and test it out. We are going to point the camera to the robot so you guys can start testing.
Let me just disconnect.
So first we will execute it. Isha, can you please go ahead and execute it for like 180 degrees or
Oh,
something.
but I just this key.
Oh, sorry. And then after that, we'll have the in-person attendees do that. And we encourage anyone who has a Spike Prime robot handy, please go ahead and try that out. And after trying out, if you either have success or some issue, please let us know.
So we'll be running the P control term demo right now. I want you guys to pay close attention to the speed the robot is going at as it gets closer to the center. Yeah.
Right.
Oh.
Pull the whole run program starts forward to the other side. No, that's not what it's saying. It's for the people here, right? In person.
Right.
Anyway, the P control gyroton is the one on the left-hand side in the shared screen. And then please also watch the video simultaneously.
So,
Was it
you
90?
guys wanna, maybe you can drop in the chat, what did you notice about this term? That was 90.
Can you run it for 180?
Okay, we'll watch it again. I remember pay close attention to the speed and then put in the chat what you noticed that's different about the turn we ran earlier. Okay, I can tell you guys what's different. So at the end, did you guys see how the robot slowed down significantly? Yes, exactly, it slowed down. Thank you, Rockoff. So it slowed down as it got to its target angle, and that's exactly what P control is for. And you'll notice it turned very accurately because it slowed down, it didn't overshoot. And even if it did overshoot, we had all this to fix it if it does overshoot. So that's one of the main differences between P control gyro term and a basic gyro term, and that's why P control is much more effective and what top FLL term.
I think someone wanted the code to be put back. You should be able to see the code right now because we have the Spike Prime app being shared. So please let us know if you're not able to see the code at this point. You can raise your hand or send us a message. So yes, we would like everyone to write the code because we want you to have it safe. And then, whenever you have access to the robot later, you will be able to test out what you're putting together right now. So we do request everyone to be following along and writing the code, please. And now in-person members are going to be executing what they have put together. So please, you can just watch the video while also having access to the code on the shared screen. So guys, you want to, if all of you are done, we can start from one end and you want to get started and you can connect. So Isha and others, can you guys help them connect and execute that?
Okay, who wants to go first? I'll go. Okay. So here, you can bring your laptop, or actually you can keep your laptop right there. So do you know how to connect to the phone? Okay, but yeah, here it's halfway there. And then here, wait, I'll just, do you know, isn't it connected to them?
So I think we're going to have, should we disconnect it?
Oh, yeah, yeah. Just. Okay, yes, it's the one. Okay, great. So, start. So right now, what your code does is it just defines the my graph, but you don't actually have a when program starts do all this, right? So yeah. When program starts.
You could go about it.
Okay, so how much do you want to make it turn?
45. That's not.
You can keep testing different
Because-
values. Once we do like straight, we can piece them together and then actually show deviations, but yeah, you can test more values. Yeah, so everybody's noticing how it gets slower, right?
Yeah.
And does anybody want to explain to me why it gets slower? It's okay if you don't remember. Okay, here, I can go over it one more time. Basically, it gets slower as it approaches the target angle so that it doesn't overshoot, and that way it can be more accurate. So does that make sense to everyone?
Disconnect.
Yeah, if you want, you can keep testing more values, or you can.
Well, if one of them wants to. Do you guys wanna? Well,
One of them. Okay.
Connect, oh, it's in connection mode, right?
oh, you have to.
Here, you can move it. Wait, I'll just move it to like.
You can try larger values. That way you can see it spin faster and then slow down.
Okay.
You have the other two numbers files as well?
They're still working.
Okay. So we have a couple of members here who are still just finishing up the code. Can you please let us know by raising your hand in Zoom if you're
You should,
done with,
you should ask one of them to like show their time if they're able.
and oh yeah, if any of you want to show your robot functioning with this code, please feel free to share that on the video. Totally optional. If you want to, you can. And if there's anyone who wants help or still needs some time to complete this, please let us know, because we do have a couple of members here who are still finishing up. So please let us know if we can help you finish up for the remote attendees. Okay. Hey guys. All right. You are muted in case you are trying to talk. So, Tyler, if you were trying to, okay, I guess that was another thing. Okay.
Oh, do you guys wanna do it?
Yeah.
So have a larger value, because that's when you can see the fast and then it becomes slow.
Which one?
90 degrees.
No, more than that. Have 360 even.
Okay.
So who's doing it now?
This one? It's the white one.
So which one?
The white one. The white one. Click the white one.
Do what?
It's on your name. Oh, okay.
Oh. So in a moment here, we're going to, or as soon as a couple of them have tried it out, we're going to start talking about the proportional go straight.
Yeah. Okay, now go.
Guys, can you make sure they are connected fine? Isha? So while we're waiting for the remaining two to finish this up, anyone want to share? Have you tried PID or any of this before? What's been your experience? Any comments? Like even proportional turning with gyro. If you've tried that, please raise your hand, or if you want to say something, you can go ahead. Okay. So our team, FRC team, we mentor a few FLL teams around here in the Issaquah-Sammamish area of Washington. And we usually start off with the basics with movement of motors, or getting motors to move, and then teaching them about movement motors and so on. And in about 2 months or so, we get to teaching them about the proportional turning and the PID based going straight. And typically in about a season, I think with a good amount of practice, they end up using the PID based turning and going straight in the competition code. So let's give it 1 more minute, and then what we can do is during the break we have, which will be in about 15 minutes. At that point, they can finish it up. Okay, guys? All right. So we are going to proceed to the next part of the presentation. It's crashing up on my computers. Yeah. We typically have a 15-minute break. It gives time for anyone who wants to catch up, and also grab some snacks if needs to be. So what we're going to do is we'll talk about what exactly is the PID algorithm. So we'll talk about that first, and then we will implement a proportional go straight, which typically is what most teams end up using. And then we will also cover the PID go straight, which uses the integral and derivative function. So let's try and understand what the PID algorithm is. Now, this isn't something, sorry, I'm going to get the video to point here. Guys, can you have a video point here? Okay. So the PID algorithm is actually something that is used across the industry in various manners. It is called a feedback controls algorithm. And all this sounds fancy. At the end of the day, you all are running the PID algorithm in your brains and making your body work accordingly throughout the day, right? That's clearly the bottom line. Now, if I were to ask you all to, whoever knows to ride a bike, there's a straight line or a curved line. Let's say it's a bike path, and you are required to ride only on that painted white line. Let's say that's your task. You're going to get on the bike, you're going to get started. And then if you find that you're going a little off to the right, what do you do? Anyone in person or Zoom, what do you guys do if you find that you're veering off a little to the right of the white line you're going to try to stay on? Yeah.
Try to realign the center.
And how do you realign to the center?
Turn the bike
Which direction do you turn the bike?
to the right side, you said here,
Yeah, it's veering to the right,
to the left.
to the left. So if you find that your front wheel is veering off a little to the right of the white line, you are going to turn the bike a little to the left to get it back on the white line. So a lot of things happened here. It's a simple action. We don't even think about it, but a lot of things happen there. First thing, you're using your eyes to visually sense and detect where the front wheel is with respect to the white line that you're going to or trying to ride on, right? So that's your sensor. So your eyes are the sensor using which you're getting feedback. You're getting feedback on the reality of what's happening. And your eyes are telling you, hey, you're veering off to the right. Now your brains, they got that signal that it's veering off to the right. It now decided, okay, I am going to correct this. I am going to turn a little to the left, which means you're negating the error. You are doing the opposite of what the error made your bike do, right? Are you just going to rotate it so much to the left that now you go off the bike path? No. You are seeing how much off to the right the front wheel is, and accordingly, that's a very important word, accordingly, you are going to turn a little bit to the left. So that accordingly is the proportional part, right? Proportional to the error, you are giving a correction. So your correction is not going to be random. It's totally dependent on how much of an error occurred. So that's the proportional part of the PID algorithm. Now, for sensors, what's the sensor that your robot's going to be using to know whether it's turning off to the left or veering off to the right? It's the gyro sensor, right? So in the PID algorithm, the gyro sensor are playing the role that your eyes would play. It is keeping track of, are you veering off to the right? Are you veering off to the left? So that's the sensor. And then how do you correct your robot? You give it different power values, right? So when you have two wheels rotating, if you give slightly more power to one and slightly less power to the other, you're causing a turn to happen. And that's exactly what you're going to do. Depending on how much of an error it is, which you're measuring with your gyro sensor, depending on how much off or how many degrees off you are from a straight line, depending on that value, you are giving a correction to the power to make it veer to or turn back to the left. Okay, so that is the proportional part. Now, the integral part and derivative part they're hard to understand if you simply talk about it in terms of the signs, like the integral and derivative and things like that. So let's go back to our human being example. Let us say you are carrying a bag of groceries on the right-hand side. You have a bag of groceries hanging on your right handlebar, just on the right handlebar. What you're going to notice is as you're riding, your bike is going to tend to keep wanting to go right because there's a weight on the handlebar. It's causing your bike to keep veering to the right. Now you have knowledge of this. Why? Maybe because you rode for a while and you know that it's happening. That's one way you could know. Or just as a human being, you know that, hey, if I have something heavy on the handlebar on the right, it's going to keep going to the right. But for a PID algorithm, for a robot, there's no knowledge like that you're using. Instead, it is going to realize over time. It's learning over time. Hey, I keep getting pulled off to the right. So maybe I should expect that it's going to pull to the right and preemptively keep seeing how often is it pulling to the right or how hard it's pulling to the right. I'm going to take corrections even before it might have already pulled, so that when you're correcting a little extra. You're not only correcting for how much it veered off, you're also correcting for the knowledge that it is going to make me pull to the right again. So please understand this very carefully, because the correction you're going to give is not going to be large here. It's very tiny. So when you actually, and when we work with the PID algorithm, you're going to come across something called KP, KI, and KD. We'll explain what those are. It's a factor by which you're giving correction. The factor by which you give correction for the integral is very, very low. It's almost 10 times less, or even more less. Even more less. That's not smart. Okay, it's even less than you would 10 times for the proportional. So if your KP is, let's say 0.5 or 0.6, which means that's the factor by which you're trying to correct the error that you saw, your KI could be 0.03 or 0.02, because you are calculating that integral need over time. So it's constantly adding up. It's going to become too huge if you keep correcting it too much. You want to give very minor corrections because you kind of know it's going to pull you to the right, and hence you're giving the correction. So that's for the human being example. Now on a robot, do you typically have that happening where it's constantly pulling on one side? There could be some reasons. You typically wouldn't happen, right? But what are the exceptional cases where it could happen? Yes.
Alignment is not symmetrical.
So,
Attachment.
okay, yes, attachment, right. So basically, if you have an imbalance in the weight of your robot, for some reason, let's say one side of your robot is heavier than the other. That is an example where you probably want to consider using a KI. You want to use the integral part, right? That's one reason. Or maybe one motor is a little more worn out than the other motor. Hopefully, you don't go to competition with things like that. Make sure you have good working motors. But let's say you're in the middle of the competition, or just the day before competition, you find out something's troubling one of the motors. You do want to use the I because it will help you overcome that difference between the two motors. So if the two motors are not behaving exactly the same, if they're not working with the same ease, the rotation is there's more friction on one of them or something like that. KI will help you overcome something like that. So using KI is not going to be necessary typically, but if you have exceptional cases like an asymmetrically built robot, which is heavier on one side, or your motors seem to be having something going on and you don't have the time to switch to new motors. These are some examples where you could use KI. So let's kind of get back into the slideshow content here. So proportional uses the current error to make a correction. This works the same as in the gyro turn earlier. Exactly. So proportional to, in this case, it really is an error, right? It's not remaining turn or anything like that. If it is off of 0, if it's not going straight anymore, that is an error you're trying to correct. So that's one point to note. And then integral uses the sum of all the previous errors. See, that's what's happening. Now let's say, for whatever weird reason, your robot sometimes tends to steer off to the right, sometimes tends to steer off to the left, and there's no proper rhyme to how it's doing that. Then you want to take care of that. You don't want to consider that, hey, it always keeps steering to the right, but then in reality, maybe sometimes it is steering off to the left a lot as well. If that happens, you want to negate it. That's why you're keeping track of all the times that it veered off as a total, as a sum total. It's a cumulative total. So it could keep increasing on one side, or if it's veering off in both directions equally, it's going to keep negating each other, and there's really no correction needed. Right? So that's very important to remember, that you are keeping track of every error, adding them all up. So over time, it could negate, and there may not be any KI correction applied at all. Or it's always veering in one, and it's increasingly adding more and more correction because it's still going to the right. Because remember, when you've given the correction, the hope is it stops veering to the right because you already gave it a correction. Despite that, if it is still going to the right, you do want to take care of that. That's why you keep track of the sum of errors. Okay, guys? Now, derivative. So this is probably the hardest thing to explain and understand. Now, when you have errors happening slowly, you're giving corrections and at the same rate, and it's taking care of the error. But if you have an error that is sometimes happening to a higher value suddenly, and then other times it's not, you want to smoothen the fact that the errors are needing to be corrected. And that's where you would use the derivative. So rather than having, another way to explain it is, you will find that you're going to have the robot go oscillate left and right if you don't have a proper KD value. Now, if your errors on the robot are not that huge, if it's just a little bit of error, then just having proportional will give you a smooth run. But if you're finding that you're using KP, you're using proportional, you're using integral, and you feel like it's oscillating, it's not really smooth. It feels like the corrections you're giving is so sudden that it's causing it to go one way and then the other way. Then you use the derivative to smoothen out that correction path. So that's the value. And it's always related to the most previous error that you had. That's what it uses. Okay. So you may or may not have understood this fully, but hopefully the human example helped make some sense of it. Just know that you will learn the PID, we will apply all three, but the highest chances are you are going to only use the proportional control go straight in your competition code. So just for example, we mentor at least 12 to 15 teams every year. I would say 80% of them end up using 80 or 90% end up using just peak control. And then there's a few who sometimes they just want to have PID and then they use it, but they have very low values, so it's not really playing too much of a role. Now, just to give you another example where this is so that you understand how the PID algorithm is used across various possibilities. Now, when you're working with, let's say there is a foundry that is heating up some metal, let's say it's iron. So iron is being held in a molten state and it's being used to manufacture some products. Okay, so maybe it's being poured into a die cast and then it cools down and then it's a product. Now, you all know that there's certain temperatures at which certain metals will start melting. So there's a minimum temperature that you need to have that iron stay in a molten state, because it's only in molten state it's going to flow. But then if you start heating it up too much, it has other adverse effects on the metal. Plus, you don't want to waste energy unnecessarily. You know that there's a certain target temperature that you want to keep. So whatever is heating it up, right? I'm not getting into the technical terms, but whatever is heating it up in the foundry, that is going to have a feedback PID algorithm running. So it knows that there's a target temperature. If the temperature of that container falls below, of that metal falls below, it's going to apply more heat, whether it's through more fire or it increases the amount of gas flowing so that it increases the heat given. It'll increase the heat by doing that. And then if it starts going beyond or a little bit too much above the intended temperature, then it's going to reduce the amount of gas and bring down the heat. So this way, with most energy efficiency, it's going to maintain the required temperature for that molten metal so that you can continue using it, but you're using just the right amount of energy. That is also a PID algorithm, right? If it tends to if it heats up faster but cools down slower, you want the Ki to be involved there. Just to get further into that example. And then the rate of change, if when you give it some heat, it tends to be very quick, whereas the cooling is not that quick, you want the derivative also to be used. So that's an industry example. So let us, at this point, we want to check if there are any questions. And then if anybody has questions, definitely please go into that. So let's see. So yeah, yes, right. Yes, I see answers to some of the questions we were asking. Thank you. So can you please, let's see. So it is 3:26. So we will start our break at 3:30, and it'll be for about 15 minutes. Like P control or there I control. Oh, okay. So there's a question like P control, are there I control or D control? So the fact is P control is the most important part of the PID algorithm. So you always want that P control. Whether you need the I and or the D is something that you can decide based on the behavior. But P is an essential part of PID. So if you're going to use a part of the PID, it has to involve proportional for sure. It could be just proportional and integral. I haven't really seen a case where you would use proportional and derivative. You usually use proportional and integral, or all three, or just proportional. Okay. So if anyone wants to, again, if you have other scenarios that are coming to your mind as we were talking about this, please share it with the group. It's kind of a fun way for everyone to remember the concepts. So anybody, mentors, students, please feel free to do that. And if you have questions about what we just spoke, please ask questions. So we will keep doing that for 3 minutes. Then we will go on a break from 3:30 p.m. Pacific to 3:45 p.m. Pacific is going to be our break. And then we'll continue with the code. Yes, we will be writing the code. In fact, I can just show that here right now. So we will get into the P control Gyro Straight code, and then we will be getting into the PID, like all aspects of the PID Go Straight. You give code for decontrol. Yes, you will have access to this. In fact, we share the guys, is it the LL3? Is that the extension for the code from Spike Prime? Well, we will share the whole project file with you guys, so you have it to play around and understand. Anyone have any other examples you want to share with the others? Anything you knew of before, or maybe as we were talking, something came to your mind that would be applicable, where the PID would be applicable? Did all that make sense? This is not easy, especially if we have younger students. We realize this is not going to be easy. So please ask questions. We're happy to repeat any part, any P or I or D. Yes.
The slide with the PID.
Yeah, we will have that open. Yeah, after lunch, or not lunch, after break. Okay, we'll have the camera facing the mat, and we will be on mute for the next 15 minutes. But our speakers are on, so if you guys speak, we will be able to hear that and respond. But I don't think we'll be watching for Zoom reactions. So yeah, please just go off mute and say something if you want to ask questions in the next 15 minutes. So talk to you all in 15 minutes.
Okay, we gotta go.
All right, welcome back, everyone. So everyone in person, let's lower the noises and get started. We'll resume the presentation. See if there are any questions. Is integral a premature correction? Yes, that would be. It's a premature correction, having known the past behavior since the whole process started. So right from when you start going straight, right, when the command's been issued, it's accumulating all the errors that are happening and keeping track of what the tendency is. So yes, in a matter of speaking, it is a premature correction, but it is taking into consideration everything that's happened in the past since the whole thing started. Can you combine PID control into one code, or is that not? Yes, you can. And in fact, you will see that we are going to be writing two different pieces of code now. The first one will be just proportional being used, and then the second one will be all three of them being used. Then can you share code after the break? Yes, so you will get access to both those versions, the one with just P control as well as the one all of PID. Okay, I think with that, the questions are taken care of. So future Martians here, please keep track of any messages coming in chat. If there are questions, just let us know. Okay. Now let's move on to P control goes straight. So we'll just talk through. We'll talk through the code and then have a Q&A, like if you guys have questions, and then you guys can start copying after that. So I would say we'll give you time to copy this code, so you don't have to start copying right now. So please pay attention to what we're discussing. So this program uses the proportional part of the PID algorithm. And like we mentioned in FLL, typically you don't need the integral and derivative. And average degrees of the drive motors are used to set how far the robot should drive forward, and the speed can also be set. And what that, the reason we have that comment there is so you understand exactly what the two input values are, or the input parameters are up there. So you see how there's a P control gyro straight my block that is being defined. And then there are two different variables being defined there. One is the speed, and the other one is the degrees. So the speed is simply how fast you want the robot to go. And then the degrees is the number of degrees you want the wheels to rotate. So a 360-degree turn would be one full wheel rotation, right? The target heading is set to 0. And that's because you always want to stay straight, right? Straight would mean 0 degrees. And Kp, which is the multiplier for your proportional algorithm, is set to 0.8. And this value should be tuned for different robots. So yeah, please remember we've found robots have used anywhere from 0.3 to 0.8. So that's a whole range. And you could even, some can even use 0.9 and 1. It simply means if you found a certain error, how much correction factor you're applying. Okay. It might seem like, wait, you always want to give a factor of 1. But then if you have too high of a Kp, you're going to end up seeing a lot of oscillation behavior. So you want it to be smooth, yet you want it to correct enough. And that's why you would use the Kp value, which is somewhere around the 0.5, usually a little more than 0.5. So 0.8 is a good number to start with. And then the error is calculated and multiplied to Kp in order to determine the robot's driving direction, which keeps it going straight at a heading of 0 degrees. So with that, let's go ahead and jump into the code. So A, set relative position to 0, set relative position to 0. Which basically means you know that rotation sensor, that's what you're setting to 0. That's what those two commands are. And then set yaw angle to 0. So you're setting whatever direction your robot's pointing at. So let us say this is when you're launching your mission, which means you have it in the start area or the launch area. You kept the robot facing hopefully exactly straight, because that's one more thing which we always teach our teams that we mentor. It is very important that you understand the importance of aligning the same way every time. When you have your code working with a certain alignment, you want to repeat that alignment every time, right? So you can use jigs or whatever mechanisms to make sure that you are aligning it correctly on the launch area. In fact, that is why they have that grid structure on the launch area, so that you can think of it as a coordinate system and know exactly where in that grid you're going to be having your robot start each specific mission run or set of missions that you're running. And the reason I was getting there is once you have placed it, you want to, from that point, go straight. And that's why you're saying set yaw angle to 0, which means from this point on, I'm just going to go straight. That's my intention. And then you're setting the movement motors and then setting it to brake. You could change that. It doesn't have to stay at brake, because if you're going to be moving straight in the same direction with different speeds, for whatever reason, it could be because you want to start off slow and then go faster. In that case, you would want it to be coast. In fact, many times when you're using this, you'll be switching that, because the last going straight block in your movement, you always want it to be set to brake. But the initial one and any intermediate ones, you want them set to coast, so that they just transition on without physically stopping and then resuming their speed. and then set moment to speed to speed. So that's what determines, it takes the input variable speed and sets that to be the speed of your movement. And then set target angle to 0, because anything that's not, if you veer off of 0, then you have an error. And KP, the factor which we set for correction, is set to 0.8. And average degrees, you start that off by setting it to 0. And then you repeat until average degrees is greater than degrees or average degrees equal to degrees. What that means is you want to keep the movement continuing till you have reached the intended amount of degrees on the wheel turn. If it makes it easier for you to understand, think of it as the number of rotations, right? So whenever you see degrees, just think of it as rotations of your wheel. That'll make it easier to understand. And then set average degrees to A relative position times -1 plus E relative times position, and then that divided by 2. Okay, so that multiplication by -1 is being done so that you have a positive value for both, and then you're dividing that by 2. A positive value or a negative value for both. You basically want to double that. You're getting the average, and that's why you're doing that. And then, actually, let me take a moment. Was that clear to everybody what that specific command is doing? If anyone here has a question, there are 2 questions, so let's check. Okay, so can we use CMS instead of degrees? So yes, if you want to use number of rotations or some other centimeters or degrees, you can do that. You just have to write your program accordingly. So in this example, we are going with degrees, so you can definitely modify that. And why KP is 0.8 for this? So like I said, if you gave a 1 correction, it's going to overcorrect both ways. So you want to have a factor slightly less than 1. That's typically how you give corrections. And then you don't want it to be so less that you didn't really give enough of a correction, so you still have an error going on. That's why there is something called tuning. So you could start with 0.8, and then you can play with values going down to 0.5. Some robots may settle down on 0.6 or 0.7, but expect to get a value somewhere between 0.5 and 0.8, 0.9. That will work. Maybe 0.8. I shouldn't say 0.9. Again, you have your members, or if you're coding it, please try different values, and then you will see that you will come upon a value which is when it is going straight without oscillating like that. That is when you have a fine-tuned value. And then okay, did that help with respect to understanding what KP or how it is set and how it is fine-tuned? So if anyone still has concerns or questions about KP, please put that in the chat. But yeah, again, to summarize that in one line, it is a value which helps decide what works best for your robot, which is why it's not always a fixed value for every robot. And it typically, so for a box robot, again, I would have to say you have to play around with values between 0.5 and 0.8 and find something that works. Let's just ask, guys, when you mentor teams, I know some of them use box robots. Did you see them settle down on a slightly different number than 0.8? Like in BLMS, I know there was one team using a box robot. Was it? I kind of recall 0.6 was what they used.
Yeah, it like ranges from 0.5 is pretty low, but 0.5 to like 0.8. So it's like different.
So yeah, there really is no golden value answer. Like for box robots, it's 0.6, and advanced driveways, it's 0.8. I would have to just say start with a value between 0.5 and 0.8, and then find what seems to work best. Okay, so going back to this specific command here about average degrees. Sorry, yeah, average. The way we are setting average degrees. It's basically taking how much did your left wheel turn, how much did your right wheel turn, get the average of those and treat that as how much you actually moved in terms of number of degrees of rotation of the wheel. Okay, next one, set the error to target angle minus whatever you're measuring for the yaw angle. Now your target angle is 0. So if your robot has veered off either left or to the right, then you will get some value being returned that is not 0. And that is an error. So that's what you're setting as the error. If you get back 0, then there is no error. You're continuing to go straight. So it just keeps. And then start moving error times AP. And this is where if you have, just trying to see where we set error initially. So we did not set error anywhere else except in that first. Oops. So anyway, KP, that is 0.8 times whatever error is there. That's what is going to cause a correction, because it's going to be either a positive value or a negative value, and it causes the direction of movement of your robot to vary based on that. If there is no error, which means error is 0, then you continue moving straight. You're not going to cause a change in direction. Is that clear to everyone? Okay. And then so going back to that repeat loop there, once you have reached the intended number of rotations of the wheel in terms of degrees, or you have exceeded it, then it stops moving, and you're done with reaching your destination and having gone straight. So at this point, if there are questions, okay, I think there's one question. Negative is no. Okay, I think that message went away, but so guys, negative would be left, correct? Negative direction for start moving. Okay. Yeah, so please go ahead and at this point you can write down this code. But as you put these instructions together, if you find that even one of them you're wondering, wait, what was that again? Please let us know, because we want you guys to succeed, but we really want you to also understand how the code is working, and when you use it to help you be more reliable in your missions. Because remember, you're going to be talking to judges. You need to have the ability to explain, for which you really should have understood all of this. And our intention here is not just to have you have the code, but make sure you've understood, and you should be able to put this together on your own. That would be the ideal scenario. Okay, so everyone in person, you can go ahead and get started with putting that code together. So we are going to run some runs, so you guys can, once you're done with putting the code together, we'll have you run across the board and make sure that the robot drives straight. Okay. And anyone who has questions on the Zoom call, please unmute and let us know, or send a message in chat.
Hi, can you explain one more time the repeat until block we are using there?
Sure, yes. So we have two variables here, right? Average degrees and then degrees. So just before the loop started, we set average degrees to 0. And then the degrees here, which you're seeing, oops, keep forgetting on presentation on old screen. So in top, you can see that the number of degrees you want your robot wheel to turn is one of the input parameters. So that's what this degrees on top is. So now you know how far you want your robot to go in terms of degrees. And then here, what you're doing is, as long as the number of average degrees is greater than the given input degrees or equal to, you want to keep staying in the loop. And within the loop, what we're doing is finding out how much wheel A has moved, how much wheel E has moved, and then adding them up and dividing by 2, just so that you have the average. Because remember, since you're constantly giving corrections, right? So your robots, I mean, ideally, if it's going perfectly straight, then your PID hasn't even kicked in, and it's both wheels have gone the exact number of degrees you intended. But if you're going on giving corrections, one of them might have gone 1 degree more or 2 degrees more than the other, and things like that. So that's why you want to get an average of the two. So that's what is being calculated in the first command within the loop, where set average degrees to the relative position of A plus relative position of B. And then because one of them is going to be negative, you're multiplying by -1 so that both of them do not just cancel each other, but actually end up being twice, and then divide that by 2. And in the next command, we are trying to check if, hey, have we veered off the path of being straight? And the way to do that is target angle, which we saw was set to 0 here. So if the target angle minus the angle that's being measured right now, if there is any value to that, that goes into error. Ideally, if you're going straight, yaw angle will return as 0. 0 minus 0 will stay 0, and there's no value going into error. That's the ideal case. And if that happens, then error times Kp, since it's 0 times Kp, it would become 0. So your start moving is not changing any direction. It's going straight. But let's say it veered off to the right. If it veered off to the right, then you do have a value for error now. And when you give a correction, you are going to cause the robot to move slightly more on one of the wheels than the other. So error times Kp is going to be some small value. And when you say start moving and you have that small value of directional change, that causes the robot to turn a slight amount in the opposite direction of where the error had occurred. And it's going to continue doing this in a loop constantly. So you're constantly measuring. If there's an error, you're constantly correcting the error, and then you're going constantly updating the number of degrees of wheel rotation that you have moved. And as soon as you reach the condition where you have exceeded or equaled the intended number of degrees, that's when you come out of the loop and you stop moving.
Okay, thank you. I have a relevant question here. We usually use rotations to travel when we are going straight or, distancing. So
Right.
how can we implement the rotations in the degree format? Because this particular program is using degrees as the travel
Now,
distance.
right. One of the reasons we use degrees is it gives you finer control in terms of how much you're going. Because let's say you use rotations. You'd use like 3.2 rotations or 3.4 rotations and things like that. I'm going to ask a question here to our students. Guys, do you know if number of degrees, not number of degrees, number of rotations supports, how many levels of decimal does it support? You guys know? Is it more than 1 decimal point? In fact, I'm going to ask this, if anyone on the call actually knows the answer to this. Like, do you know if 2.45 is a supported value, for example?
2 digits, if I'm
Okay. So yeah, if it is 2 digits, then that gives you a good enough resolution that you can work with. So we kind of stuck with degrees because it was easier to explain and easier to work with in terms of the numbers. But you would basically take an input of, let's say, instead of 700, let's say we want to use 750 degrees, which is 2 whole rotations and then 30 degrees after that. And let's say that is 2.13 or something, 2.13 rotations in terms of rotations of the wheel. So your input would be, instead of degrees, it would say rotations, and the value that you give it in this example for 750 degrees would be 2.13. So you would go in here and your average degrees would be, so that's where you'll have to figure out a way of modifying or translating the relative position to number of rotations, adding the two up, and then dividing that by 2 to get the average.
That's the challenge we are facing. We are a team who's from 3 years who is trying to get an advancement and include PID, but then the same thing is happening. Either this is the first time I'm seeing degree usage instead of rotations, so I might try to implement it. But then I also want to understand, if in case we want to go ahead with 2 rotations, how can we do that? If you have any codes which can show us or support us, that will be great. If you can pass me on that thing later.
Okay,
If
yeah,
not,
so right. So right now we definitely don't have any code that uses rotations. But I'm going to do one thing though. I'm going to ask our students, because we, all the students, they mentor the FLL teams. So guys, have you in the years of mentoring FLL come across teams that modified this or used a version of this that utilized rotations of the wheel rather than degrees? That's one question. The other question is, do you see how would you, relative position is being used there to know how much it has rotated. If you want to use rotations in terms of that decimal like that, do you guys know what you would do here?
The thing is, like, with degrees, you just have more accuracy. Like, you can get it up to a more like precise
Right.
point. So that's why there's never really a reason to change from degrees to rotation.
Yeah, so what we do is whenever we mentor, we tell them to go with degrees for multiple reasons. One, they don't have to deal with decimals and they're dealing with whole numbers, so it's easier to understand. And given that these are typically, fourth, fifth, sixth graders, we want them to start thinking in terms of degrees and how 360 degrees is one rotation and all that. So, but I can have some of our members try this out to see if there's a way in which we can achieve this with rotations and get back to you on that. If you
okay.
don't mind,
Sorry to interrupt.
yeah.
We don't mind going with the degrees. I'm just trying to understand here so that I can pass it on to my, team, little ones. If I want to, suppose if I want to travel 10 centimeters, okay, distancing. So when you are talking, you are dealing with degrees. How do you decide that? You just try keeping increasing degrees, or how do you calculate the number of degrees?
So we kind of make this an exercise, a fun exercise for them. So we ask them to measure the circumference of the wheel, and then we tell them that, hey, 360 degrees corresponds to, whatever. Let's say it is. Pardon me. Let's say it is about 6.5 centimeters or 7 centimeters. So we tell them 360 degrees translates to 7 centimeters. So if you want to travel 10, you run the math, and then they will come up with the degree value and use that. So that's how we do it.
Okay, thank you.
Sure. But yeah, if you want us to find out about the position, like the number of rotations, please drop an email at FRC manager to get email.
Sure. Thank you.
Sure. Okay, so what does changing the KP from 0.8 to 0.5 actually do? All right, so let's get into that. Now, see, if you see here, what the way KP is being used is, it is applying your corrective change in power by multiplying that factor KP with the actual error that happened. If you have a higher value of KP, it's going to give more of a correction. And if you have a lower value of KP, the amount of correction is less. So if you have too low of a value for KP, it may not even correct the error enough. So it's still not going straight. It's still going in the wrong direction. And if you apply too high of a KP, it's going to cause the correction to be so high that you now have to recorrect it in the opposite direction. That's when you're going to start seeing oscillating behavior. So one way to go about this is you start with a higher value and you work your way down by lowering the KP value till you reach a point where it stops the oscillation. So that's one way to do that. And guys, if you have any experiences you want to share about how you've had the teams do the tuning, if it's different from what I said or something, please share.
No, it's
Basically like that, right? Okay, yeah. Does that help? Okay, we will continue there. So hopefully you've all been able to get the code written down at this point. I know I've been talking, so maybe you guys didn't get a chance. Let's check in person and then we'll check with everybody on Zoom. So in person, do you all have this code written down now?
Yeah.
Yeah, okay. And then let's make sure everyone on the Zoom call did as well. So if you want more time to complete copying down the code or writing down the code, please raise your hand in Zoom. Otherwise, we will move on to the in-person people downloading it, executing it, and then we'll watch how that works. Okay, so we don't have any raised hands, so we'll continue with the plan. All right, so did you guys want to go ahead and just start? We don't have to run it from our laptop. So this time, let's start from the right-hand side. If you want to download the code, and let's have it at one end, and let's have the camera face time. Guys, you need to start helping with the execution now.
Do we remember how to connect to the hub? Okay. So who wants to go first?
They're starting from bottom.
Oh, yeah.
Can you keep it on one end? And then can one of you, I won't block your view, but as it's coming in, just give it a little knock. Well, have it from this way so it can go. And then as it's coming here, give it a little knock so that you can show it correctly. Yeah.
Okay, so we'll make it go straight and then I'm gonna like try to push it off course and you guys are gonna be able to see how it automatically corrects itself to keep going straight.
It's hard from there, I can try to. So degrees of rotation, I would give it a good number, like you can give like 4,000 or something. 500, it might just move to like just out of the launch area where it's. Yeah. The hope is to try to get it all the way there, so you can see how it continues to be straight. Not wrong.
I'm just checking.
8 degrees with 0. That's correct. Initially. That's initialization. Okay, does the second person want to try while he's confirming? No? Want to try? Okay.
Oh, that's it. Oh.
Again, if anyone has their own robot, for those who are on Zoom, please feel free to run it. And a fun way to see the PID kick in is as it's going, intentionally just give a sidewards push on the back or the front of the robot, and you'll see that it will correct itself and go back to being straight.
Okay.
Oh.
I just moved it and now it's going back, right? Did everybody see that? You guys can get out of the guys.
Okay, it looks kind of wobbling.
So
That's
good,
because.
good
yeah.
observation. Yeah.
Yeah, that's a good observation. That's because it's constantly trying to correct whatever errors might be occurring. For example, like if this wheel accidentally slips a little, then it's constantly correcting when slips like that or
Is there a way to go like straight enough so that you can't really see it?
Right, so that's where you would play with the KP value, exactly. So as you might have all observed, when it was going straight, I'm not even talking about the one where Isha just tried to knock it off course. Even when it's just going straight, you could see that it was going a little to the left, a little to the right. It was kind of like a zigzag movement, tiny bit. And that's what you can tune by playing with the KP value, by making it lower or higher and see if it can make sure that it's going straight. You shouldn't be able to tell that there's something beyond simply going straight that's happened.
I'll do it.
Okay, can we have the second person run the program now?
Yeah.
Yeah. Right. How many degrees is it going? Must be a large number.
4,000.
So 4,000, I guess, is too high. So maybe we'll try 2,000 next time. Yeah. Although I'm surprised 4,000 went not long. Okay. All right. You want to go next? Just for fun, we'll have it go the other direction.
Yeah, do you want to try knocking it off? You guys can like.
Yeah.
It's pretty.
What if you just held it like this for a bit?
If you held it like that, then it would keep trying to fix it. But if your like hand was holding it so that it couldn't fix it, then as soon as you let it go, it would fix it. But it can't like fix it while you're.
So you want to come closer and,
You just, like,
or, I mean, wherever you next.
Probably like going back to the.
So of course, if you slide it sideways, then it has translated, and that's probably a good thing to talk about. So during this test, the camp attendee here who was knocking it off course, what he did was basically move the entire robot sideways by making this wheel skid sideways. So that is a translational error, right? Where it just moved sideways. Now, that is not something you'll be able to fix with just the proportional control, because what's happening is you are essentially replicating something like lifting the robot and moving it to a parallel line and then keeping it down. Now, if you had the PID algorithm and for some reason the errors kept it going to a parallel path, the eye would help bring it back on path, but not if you literally pushed it sideways, because then you did not collect all the errors that would have been corrected, because it just was literally displaced along the side. So we have one more member here who's going to run it, and then we will move on to the next one, or we'll move on to questions. Oh, we have some questions in chat. Would you want to clamp the KP value? So we have, I mean, frankly, we have not tried anything like that. We have just manually played around with it, settled on a single value, and stayed with that value. Let me ask you guys, just check what clamp would do. It's a mathematical function, what it would do. And would you want to do that with KP? What would you gain from doing that? Can you guys quickly check clamp? You should see the text messages. Guys, I'm hoping you're watching the questions and trying to find the answers to that.
Yeah.
Yes.
Are you connected to the hub right now? Yeah. Oh, okay. Yeah, you can run it. And one of you guys, like, turn it around. Oh, yeah. Wants to try to knock it off course.
KP gets added straight to motor power with nothing.
Does anybody
happening.
didn't go want to try and knock it off course? It's pretty cool. Okay.
So
Yeah.
not quite clear. I hope I answered the question, which is you're just going to multiply the error with that factor and then yeah, multiply it
Okay, yeah, so you see how like,
to multiply.
Wait,
Yes,
I mean, it was definitely.
it simply gets added to multiply. That is correct.
I mean, you can experiment with the speed, it's just like when you put it that fast, it gives it less time to correct the error, which can sometimes make it a little
Okay,
less
if
accurate.
no one else has questions
But I mean,
about
we're just experimenting.
the proportional
That's what you guys put.
control gyro straight, we can move on to the next one.
Oh.
Just one message. It is a fixed value. Okay. So let's go back here and look through the code to see what is different. Now the first part, which is you defined the my block, that is the same. Speed, the degrees, so that's all still the same. And you just set the relative position for both A and E to 0. No changes there. Yaw angle is set to 0, same thing. And then the next few commands right up till set target angle to 0, they're all the same, including that one. Average degrees set to 0. Okay, and then starts the next set of things. Actually, I'm going to stop because we have the members here still discussing the previous program, so we want to give them a moment to finish. So I'm going to stop the PID for just a moment. Sorry, guys, I didn't realize you were like working that out.
Oh. Yeah.
What if you like shift its direction like a lot? Because instead of just like
The thing is, to do that, you would probably have to push up the robot and shift it. And if you pick up the robot and put it down in the complete place.
No, actually, let's run that. Let's run that.
But yeah, we can.
So, yeah. So if we can execute, re-execute that program. So for those online, the question was, you know how we've been pushing on one of the edges of the robot, or one of the corners of the robot to cause it to veer off direction a little bit. The question here was, what if you push it so much, like maybe 90 degrees or something? What happens then? So we can show what happens.
No, you can just play it. It's already down there.
Oh.
Oh, sorry.
Oh,
Yeah,
yes.
of course.
Oh,
it's-
it, like,
yeah. So
see, he like turned it around. Okay. So yeah, it does
So,
correct, but like.
even when you pick it and place it back, it's gonna go back because it knows what the yaw angle was when it was reset to 0. And it's always intending to go back to yaw angle of 0. And then that's what it's going to do.
change the pitch or something.
The pitch,
Like using.
there's, the thing is like. For FLL, the pitch doesn't really change it much, like when it's just going around, unless there's like bumps, but there usually isn't. So.
Gaps.
Yeah, as you can see, nothing on the field causes you to go over hurdles, right? Like I said, 4 years or 5 years ago, when you guys did, which was a Cargo Connect or the one before that. Anyway, so there was one where you had to climb up on a bridge and then end up literally on the middle of the between the two fields. In fact, you could knock the other robot off. There's some component like that.
Yeah, I was think that was
Not Cargo Connect. Which was the one before that? There was one before Cargo Connect.
Yeah.
Anyway, so there, what teams used to do is when it was climbing up the ramp, it would change that other angle, right? So they would measure that, and as soon as that went back to 0, they would stop because that way you are confirmed to stop right on top of that bridge.
So like, basically right now in the code that we're running, there's nothing to correct the pitch. But the thing is, there doesn't really need to be any.
City shaper, that was the one.
Does that make sense? Yeah.
Okay, I see a few chat messages, so let's quickly take those. KP is potentially a music factor. Yeah, I think, yeah, that's one of the technical explanations for what KP is. Okay. Before that,
Change the and move the robot. Does it change the way that
some reason ours is important. I tried
Goes back to the-
1, just never correct.
the way that
Yeah, so it basically will change the speed at which it corrects itself. Because the KP it's multiplied by the error to determine what speed to correct the
Just
error.
never correct.
So if it's lower, that means it's going to go slower. If it's higher, it's going to go.
So one
You
of
guys
the
can
first,
experiment with that.
as I want to talk to you. So one of the first things I would suggest is, are your drive motors exactly A and E, or is your code set to the right drive motors? That's one thing you should be checking. And let's see, what else could be different? So apart from that, yeah, you want to make sure that your robot is set up where yaw is what measures the turning of the robot. So if your brick is on its side or lengthwise high up, then you would not be using yaw. Instead, you would be using either pitch or roll. So that's another thing you could check. And then degrees of, so if it is going straight, then you know that your drive motors have been set correctly. Checking the yaw angle, and then making sure that you are setting the target angle and average degrees, like the initialization to 0. That's another thing you can check. Let's see if there was an update to that message. Yeah, it may not be the tuning values, it may be something else. If you're not seeing any kind of correction, because if you had too high of a correction, you actually can see the robot start spinning around in circles. That means you just have too high of a correction. And there are other things that could cause that, especially when you're working with PID, not just the distortion. So to the person who had that message, we'll be happy to work with you even after the camp if you're continuing to see that issue, and you can address that if you're not able to get that look. Okay. So going back, you had a KP of 10. Okay, that is really, really high. That is, I would say it potentially has something to do with how power is being calculated and applied to your motors. Okay, all right, yeah, thank you. So let's move on to the next piece of code. I think we were already talking about it. I'll just repeat that for the benefit of those who are trying to get the other code to work here in person. So guys, this one is the complete PID, which used I and D as well. So as we were going through, the definition of the my block remains the same, and all the code right up to average degrees being set to 0, they're all the same. Now we're introducing a few new variables. Integral is one, derivative is another one, and then last error, that's another variable we introduced. And then in terms of the K or the tuning values, we introduced KI and we introduced KD. So as you can see, KI is almost 40 times lower than AP. And KD is quite a bit lower. It's about 2.5 times lower than KP. Again, these are values you're going to have to play with and figure out. Now, just to get this part out of the way, when you are playing around and trying to figure out values, you want to go one by one. You start with KI set to 0, and KD set to 0. Find a good value for KP. Then you leave KD set to 0, but you start increasing KI from a very low value like 0.01 or 0.02 and go from there. And after you have what you feel is a good KI value, then you would go to KD. But frankly, what happens is in FLL, if you start trying to get all three of these values, the need for KI and KD is so rare and so little that you won't really come up with a meaningful value. So my strong suggestion is, unless you have a very good reason like a lopsided robot or motor issues, just stick to KP. You can try KI, but when you start getting to KD, at that point, you're just doing it for the sake of doing it. But feel free to try and play around with it. These values that you see here are kind of what might generally work. So you could use those as starting values and then increase it, decrease it a little, see what happens. If you have too high of a KI value, it's going to start running around in circles. Okay, with that part out of the way, let's get back to the code. So we have like 6 new variables in there, and the repeat until the criteria for going into and remaining in the loop is still the same. And the set average degrees also remains the same. And the error also is set the same way, which is target angle minus the current yaw angle. What you now see is the variable integral, which you had initialized with 0. So change is an interesting thing. It's neither a specific add or a specific subtract, right? It is basically combine the values. It might add, it might subtract, depending on the sign of what you're adding to it. Well, depending on what value you're combining with it or changing it by. The reason you use change there is the error value might be positive or it might be negative. You're simply including that into the current value of integral. So it could decrease or it could increase depending on the sign of error. And then derivative, if you recall, it's always based on the most recent error. So for derivative, you are going to set it to the current error minus the previous error, right? So let's say right now I'm trying to correct the instance of veering that just happened. You had saved the previous time that you gave correction, what had happened, that was saved into last error. So you're subtracting that from the current error, which then you can use. So if the errors happen in opposite directions, they're going to cancel out each other, right? If it happened in the same direction, wait, let me reword that. So since it's a subtraction, it's going to be the difference between the previous error or the current error and the previous error. Okay. And then when you get to the start moving block, you are giving 3 different corrections by summing them up. The first one, error times KP, that's still what you already had done for the proportional control. Now, to that, you're adding integral times KI. And remember, integral is the sum of all the errors that have been happening, like the cumulative sum of those. And then to that, you again add derivative times KD, which is the difference between the current error and the most recent error before that. You're combining all of this and giving the correction in the angle to start moving. So the rest, it basically functions the same way. It's just that you now have calculations in place for 2 more corrective values, and you have added those 2 more corrective values to where you're doing all the correction. Okay. So there's one chat message. Let's see what that is. Okay, that might have been a message. Okay, so I know that sounded complex. The D part, especially, we do struggle with getting that across, especially with the code. You have the calculations. The calculations are straightforward, but for understanding, yeah, you use a human example. I think it helps understand it a little bit. So now we're going to request you all to go ahead and you could make a copy of the other my block, edit it with the new definition name or my block name, and then add the other piece of code that you need to add to it. So please go ahead and do that now, and then we're going to run that. Yeah. Yeah. Then let's fix it. We knew there was a screenshot taken from. So we are being told that we are checking something about the loop with respect to last error. So please bear with us. Go ahead and get this in place. We might ask you to make a correction with respect to the last error. You guys want to switch the code because I think the code has the right one.
Yeah.
And we should actually put the screenshot. Wait, they don't have a way of copying it if we take away the screenshot, but they're seeing this one, right?
Yes.
So you guys can analyze the code, but let's have this being displayed so that they have a place to copy the code. So for everyone on Zoom, please go ahead and continue to update your code based on what you're seeing here. Meanwhile, we're just analyzing something in the loop.
Yes, it looks fine.
The answer has to be updated with current. If you see set last error. Did you guys just adjust it? Okay. That was all. Go ahead and explain that.
Fine. Okay, so the error was that last error was not getting updated within our loop. So essentially last error will just stay 0 when it was set like up above over here. So we added a line that says set last error to error right before error gets re-updated to be the target angle minus the yacht angle.
To be louder.
So that way, last error will now actually reflect the error before error gets updated with this line of code here.
Thank you. Yeah. So hopefully everyone heard that. I think that's a footprint. Oh wait, there was an update now. Yeah, so Steve, to your point, you know that in reality that is actually a smart thing to do because you want to be careful if integral gets very big, it can start having all kinds of adverse effects.
You sure do, and weird things
Right.
can happen. You know,
Right.
you just never know. You know, a stall, a lockup, some kind of weird thing, and all of a sudden
Right.
it's out of control.
Yeah. So, yeah, that's definitely great advice there. So for everyone's benefit, basically what this means is because you're going on accumulating the amount of error that is occurring, there could be non-typical situations, like maybe your robot got maybe something that you were carrying in a previous mission was in the way and it caused your robot to physically get moved towards the side, or I'm just making stuff up, but things that you wouldn't typically see. And now, every time there's a measurement, it's dealing with large error values, which are accumulating very quickly, adding up very quickly. And it might end up reaching so high of a value that now it's just spinning around and things like that. So by having a ceiling, you're making sure that it can only affect to a certain extent. So when it gets really impractically high, you stop caring for what the integral is saying. Steve, thank you for that. And then, let's see, so if everyone's continuing to copy the code, please keep doing that. Meanwhile, I would like to correct that screenshot. Please bear with me for a moment. I'm just switching back to the slideshow. Okay, maybe I'll do this later. So let's switch to the actual code in Spike Prime app for you to copy from. But before we share the slide, we're going to make sure that we have the fix in that presentation. This is the correct one, and as Arvind mentioned, this was the line of code out of the command which was missing, the one which makes sure that last error keeps getting updated to the current error before current error is reevaluated or recalculated. Okay. So a quick check, everyone in person, have you all updated your code to reflect this? Okay, so you guys are ready for some testing? Not yet? Okay, you guys keep working. So those who are ready to test, you can go ahead, connect and try that. Future Martians, can you guys please start helping them with running the test? And everyone who's online, please let us know with a thumbs up if you want some more time to complete this code, the coachings for PID.
I'm good. I don't have the fortune of having a robot.
Okay.
In fact, my team's never done any kind of serious calibration. You know, we're just not that sophisticated.
No, I mean that's the beauty of FRC. So everybody starts somewhere, and then you can keep learning, and then getting more
Yep.
complex. On that note, I'll just share a funny story with our team. So we actually started with the FRC team with a bunch of 8th graders. And the reason we got this team created was the local high school's FRC team was so big that they couldn't take half the applicants. And so we started this team. And yeah, it's amazing how much they've all learned. So we have some of those members who are now seniors. And this is their 5th year of the FRC, and it's really amazing how much this program gives in terms of learning.
Yeah, the sophistication that you're at is significantly beyond where the 4-person team that I work with is.
But it makes a difference to every student who's part of these programs, in whatever capacity, whatever level it is.
I need to finish my first.
Can you?
Oh, yeah.
You want to taste your food?
Excuse me,
Yes,
I have a question.
sure.
I understand that your team in the institute also does mentorship for other FLL teams. So what are the requirements? Will they be able to forward our email?
Definitely, yeah, please do email us. Are you a local team in the Eastern state?
We are a New Jersey based,
New Jersey.
I'm a parent-led team. We are a parent-led team actually. I started the community teams, 2 of them,
I see.
with my kids, and then later on it moved on to bigger level. So we are definitely looking for some mentorship this year to do advancement. We've reached up to certain level last year and got stuck with few things, and we would like to go beyond that level with both the teams. So we're looking for some mentorship on certain advancements like advanced attachments and advanced robot and advanced coding like PID, what you did today. So that's
Yeah.
the requirement.
Okay, let's definitely talk. You can email us at frc9023@gmail.com, which is where we send the emails from for the camp. So please just reach out to us. We can have a Zoom call with the team and understand what you're trying to gain. Because for mentoring, when we talk about mentoring, we have at least 1 session per week with that team throughout their season. That's how we do mentoring. And if you need sporadic help with certain concepts, we can definitely do what we call assisting a team, which is not necessarily on a weekly basis, but whenever you need help with a specific topic or a concept, that's another option also. So we can talk about what would work well for your team.
Sure. Thank you very much. We'll forward the email.
Sure. Yeah. So for everyone who's on, if you have a robot that you can try this on, please go ahead and try it. Otherwise, this is our last slide. But we're happy to. I mean, we're going to stay here at least 5-10 or so. So once you have completed this code, if you don't have a way to run it and you want to do that in future when you have access to the robot, that's fine. But if you have questions based on what we've covered, we can talk about that now, or maybe after 4 or 5 minutes. If you have anything you want to talk about in general, we're happy to talk about that, including future edition and founder edition and things like that, or some other technical topic. So for the ones who are here in person, are you guys able to run that code?
I need help with the last one.
Last one, okay. Can you guys help them?
Hopefully this one. Oh, that one. I don't know. Oh, yeah, that is.
Okay, just hit the. Okay. So there is.
Yeah, if you have the code written, feel free to leave if you want to, and if you don't have any questions. So we will be sharing the presentation, and we will be uploading this recording. Please give us a couple of days to go through and do this. But we will upload this to YouTube, and we will share the YouTube links with you. And I believe this year we're going to try and share the AI summary notes as well. I don't know how helpful it is, but it kind of gives you a quick summary of what was covered, at least. It doesn't really go into the technical details because it tends to keep it more like a summary. But we will share that the presentation and YouTube links. Yeah, if anyone's leaving, thank you so much for joining us. Wish you all the best for your season. Yeah.
You guys have a first open.
Wait, coach, can you show how you did that start block?
Oh, yeah, yeah.
Like the green part.
Wait, where did you get it? You mean this one or?
Go back to where you were.
Oh, sorry. Oh, how was it built?
Yeah.
So it is a mathematical function, which is, so let's go to operators, right? So see, you can see how it is really two, it's a summation of two, but then in the second one, it's again a summation of two. So let me show how that's done. So you bring this here, right? And then keep watching. So you get that, and then you're going to take this one and you put the second operator in there. That's how you get
Okay, so 2 plus.
summation of three things. That was the question, right?
Yeah.
So you guys still trying to finish up the code? Are you guys having some challenge or finish it? Okay. Feel free to go ahead and run it if you want. You guys just help with the field management.
Someone else can, yeah, AR, and you guys.
Yeah.
Oh, there you go. Okay, you should press.
There's so many machines there, aren't there? I guess there's still something. Wait, is this how it's supposed to be?
Yep.
About this thing about fields of easy file.
Yeah, it's fine.
How delicate is it?
Some of them like they have a lot of loose.
This is a very delicate.
Yeah.
Transporting this is a pain. Yeah.
Some of them have like loose.
There are some more missions.
Yeah, there's some. I mean, we got this, I think, a week ago. They've just been, students have been building whenever they have time. So there's one here, there's one here.
There, yeah.
Thank you. So yeah, I think there's at least 4 or 5 large ones. Okay, so you saw how it eventually corrected and went back, but it needed more paths for the correction because
At
when
first,
I pushed it.
almost, it like overcorrected. Do you remember?
I think the B may be causing some of the behavior. It's like overcorrecting and then correcting back slowly. But yeah, like I said, the fact is proportional controls should be really good enough. And even now here, because you guys haven't tuned it, what you can do is set the KD to 0 and just see how the KI works before you start getting to KD. Yeah, if there's any general questions, please feel free to ask now. We can talk about anything. Oh. Have a couple of you tried this out now? 2 more people remaining, or did everyone try? You want to try? Or
I already tried.
you already tried it? What about the person from Microbot? No?
I don't know.
But his laptop's still good, right? But
Yeah. Well, ask me.
you tried, right? And did you try? Are you
Yeah, I
trying?
already tried.
Good. Okay, then. So everyone here in person has also completed the code and tried it out on the robot. So I will say if anyone has questions, please bring it up now. Otherwise, you have our team email. Anytime during the season, if you have issues or you have any specific questions, please feel free to reach out to us. We'll be happy to help. We like mentioned, we have almost all our members have done FLL, FTC, and now they're doing FRC. So we'll be happy to help. Okay, so everyone have a great season. Wish you all the best and great learning and fun. Thank you so much for joining us.
Thank you for doing this.
Yeah.
Really useful for us.
Yeah, you're welcome. So I hope you guys had a fun time. Kind of reminded you of the fun you've been missing in the off season, right? Come on, when you push that robot and you see it go back on track, that is fun. Guys are ready to try out something new this year, or you're gonna work with the? Did you guys try box robot last time?
Last year we were gonna do a box robot, but it was too close to competition time, so it's one.
Yeah, if you have new ideas you want to try out, this you guys have a few years. You guys have this is your 3rd year or 2nd year? I know for
This
you
is my
individually it's your 3rd year, but as a team it's 2nd year, right?
Yes.
Okay, and you guys also are 2nd year on the team. So yeah, you guys, this is a good year to try out something different if you have been wanting to.
4 bars. Okay.
So instead of the
No, that's
current format of FLL.
I can't even solve that mission with my hand. I can't even solve it.
All right, then we will go ahead and end the Zoom call at this point. Thank you, everyone, and all the best.
They look so.
But before I do that, if anyone was still
I can.
trying to write the code or finish the code,
Yeah.
please let us know. We can stay on if necessary. Okay, I don't see any reaction or any messages, so we will go ahead and wrap this all up.
I think it's a one-line thing. Wait, how can?
Thank you, everyone. Bye.
Yeah, that's so.